Hello students, welcome to this the next module of this particular course. So this talks about the delay more significantly. So this particular module will talk about the delay, which means the performance of the circuit also. So I've written it as a CMOS delay, which it means that it is the CMOS related circuits and its delay analysis for the digital circuits, which we have designed using the CMOS circuit families. So moving ahead, so what we'll do is we'll quickly look at some of the definitions and then go back to our primitive circuits, digital circuits, which is the inverter circuit. Right, so this is a definition of the propagation delay here, what I've drawn. So let me pick up my pointer. So yeah. So this is the propagation delay falling and then propagation delay rising, right? So if I have an input signal here, so this is the input signal. So there is a little bit of a ramp signal and then it's steady state signal of logic 1, and then it falls back. So this is the input signal with respect to the time domain. For a given circuit, so let's we don't know what circuit it is, but if you apply this particular input to that particular circuit, the output of the circuit behaves like let's take an example. The output of the circuit behaves like this or gives this kind of a response. Then you can see that the output is kind of much it arrives after some time with respect to the input signal. So the output rises initially and then it reaches to a steady state logic 1 and then it falls back. Right, so in that case, if I want to define what is a propagation delay rising and propagation delay falling, so whenever the output starts rising, so this particular, the rising, the output is actually rising from 0 to the logic 1 here. So we consider that as the rising definition. And then the propagation delay definition turns out that whenever the duration to which the input, whenever the input is at 50% and the duration till the output is 50%, we say that is the propagation delay. And so that is the propagation delay. The P and D stands for that, and then the rising one is with respect to the rising output. So the propagation delay rising, the term TPDR, which is nothing but the propagation delay rising, defines the point where the input is 50% and then the output rising is 50%. Right. Similarly, the propagation delay falling will be when the output is actually falling and it has reached to the 50% of its falling output. What the 50% means, whenever it has gone to a 1, the digital logic 1, which means it is 1 volts or any other 5 volts. And the 50% represents either 0.5 volts, and if it is 5 volts on this side, if it is 5 volts, then it should be 2.5 volts. So the 50% of the maximum voltage. So whenever it starts falling, whenever it has reached to the 50% of the maximum voltage, so the duration from the input 50% to that of the output 50% will be my propagation delay falling. Right? Hope this is clear. So the input here, I have taken a kind of a ramp signal, some kind of a rising signal here and then some kind of a falling signal here. But let's say that if it's a step input, it's a completely a step input, then in that case, the output voltage here, if it turns out to be very same as what I have drawn here, then for a step input, it will be nothing but wherever the step input has begun, and then the output, whenever it has reached 50% of the rising one. So we will take that as the propagation delay rising, right? And then we have another definition called as the contamination delay and contamination delay falling, and then which we will look into the next slide. But most often we will come across, whenever we come across the delay or the performance, it is basically the propagation delay falling and or the propagation delay rising, and also the average of that for a circuit. And if in a circuit if it has multiple paths, then we take the critical path being the path which has more number of gates. We take that as a critical path and then determine its the propagation delay characteristics. And it could be both the propagation delay rising and then the propagation delay falling for that particular critical path for the given circuit, right? Let's proceed further and then see the contamination delay example. Just to see the example, it is very similar to what we had done for the propagation delay falling and rising. It is again nothing but that 50% and 50% of the input, 50% of the output, and then the duration of that will give me the contamination delay. But the scenario is slightly different here. Let me take an example here of a 2-input NAND gate. So my inputs are A and B here and output is Y, right? So let's take a very simple example of 0, 1. If I provide a 0 and 1 to the NAND gate, so if it is 0 and 1, my output will be nothing but for a NAND gate, it will be nothing but 1, right? Now if tomorrow if I change from 0 to 1 here and then from B1 to 0 here, my output should stay to 1, right? It should not change. But what happens is at the input side, if A changes from 0 to 1 quickly, but B doesn't change quickly as the A has changed. B takes some amount of time to change from 1 to 0. So in that case, this particular middle portion, let me pick up a different color. So this particular middle portion where A and B are 1 and 1, right? My output, when the inputs of a 2-input NAND gate is 1 and 1, my output is actually 0, right? So it actually goes from 1 to 0 to 1. Right, so this is a contaminated output. So this is not really the output we are looking for. The output is actually the steady state output we are looking for is 1 and 1. It stays to be 1, but there is a contaminated output. So there is a 1 here, and then there is a contaminated output for a short duration, and then goes back to 1. Right? If I draw the timing diagram, this is what we will get. So this particular contaminated output, as the name says, it is a contamination, and we really don't want this, but it is there in the system because of our whatever the design we have done, and because the B is reaching 0 late, right? So this is actually reaching 0 very, very late, and that's why we are getting this contaminated output. Now with respect to the input and then the output, if I draw that 50%, the input rising and then 50% of the output rising with respect to this contaminated output, we should then say that that is a contamination delay rising. And similarly for the contamination delay falling, will be nothing but with respect to the rising input and then the output, it is falling. So the 50% of that will be my contamination delay falling output. Right. So remember that for both propagation delay falling and propagation contamination delay falling, it is always the output which is falling, right? And then similarly, contamination delay rising and propagation delay rising, it is the output. It is defined with respect to the output which is rising. Right. Hope it is clear. So moving ahead. There is one more definition called as the rise time and then the fall time, which I have specified here, TR and TF, which is nothing but the rise time and fall time. And with respect to the output signal, again, this is the time axis, and then the y-axis is the output axis. The rise time is nothing but when the output signal is rising, and then the duration it takes to, this particular portion from 20 to 80% is my rise time. And then from the output, when it is falling from 80 to 20%, that will be my fall time. So don't get confused with the rise time and the fall time with that of, and then mix with that of the propagation delay falling and rising. The propagation delay falling and rising is with respect to the 50% of the output voltage level, whereas the rise time and fall time is with respect to the 20 to 80%. Right, so do remember that in our when you are calculating or estimating the rise time and then the fall time for different circuits. Right. So coming back, we have done this definition, and what is the use of this particular definition? Of course, it helps us in characterizing the delay of a circuit, especially the propagation delay falling and rising, which will help us to characterize the delay of the circuits. The contamination delay falling and rising is kind of very important. So if you remember the contaminated output, it should not get captured into the next set of circuits, especially when we are doing the sequential circuits. We have to characterize the setup time and then the hold time appropriately, such that this contaminated output doesn't get carried forward. So that is one thing. And the rise time and the fall time, it is generally defined with respect to the input characteristics, to the input signal characteristics. So if suppose I have an input of 20%, the rise time so and so, how should the output behave? Right? For a step input, I think the rise time will be 0 for a step input. Right? So the rise time will be 0. But generally what happens is whenever we are giving a signal, or whenever we are getting the signal from the clocks, or whenever we are generating a new signals, generally we will have some kind of a ramp signal, right? We will have some kind of a rise time, right? And then similarly, if I want to bring the output to some other level, we will have an input which is generated, which will have some non-zero fall time. So that is the use of all these particular parameters. But now how do we fit in, or how do we characterize an inverter circuit with all these parameters, right? So I have to go back to my circuit, I have to go back to my inverter circuit, understand the parasitic elements, the parasitic capacitance elements, and then see whether I can calculate, or whether I can characterize some of this delay parameters. Right, so that's why we have come back to our the standard primitive inverter circuit. Although it looks a little bit overwhelming, so let me try to evaluate this, what I've drawn. So I have an inverter here, so it is nothing but the PMOS circuit. So this is PMOS and then this is NMOS. PMOS, looking at this particular bubble signal, we will know that this is a PMOS circuit. And then the NMOS, the gates are tied together and then given to this as an input. All right, and let's say that for an NMOS, I've drawn an NMOS here, N plus and N plus. And let's say that this is my output signal. So I labeled it as Y. So this is the Y here in the cross section. And there is a gate, and then there is of course the oxide, and then of course there is a body. Body is grounded. The source is also grounded. Right. Now, how many capacitances do we have? So one capacitances, I can easily see the depletion capacitances coming from drain to body. So this particular capacitance I'm talking about, drain to body in the NMOS side. So I've written drain to body capacitance on the NMOS side, right? And I also have a capacitance on this particular side, which is source to body on the NMOS side. So C, S, B and N represents the NMOS, S and B represents source and body. Similarly here, the capacitance DBN represents the drain to body capacitance, and then the NMOS here. On this particular side, this particular capacitance, if I look at it very, very closely, I know that the source is anyways grounded and then the body is also grounded. So on both the terminals of the capacitance, both the terminals of this particular capacitance, it is grounded. All right. And similarly, if I look into the gate side, I will have a capacitances here, the gate to body capacitance or gate to the channel capacitances, which we had seen in the previous module that as the VGS changes, or as the VDS changes, we can also appropriate apportion that into CGS and CGD. Right, so I'm going to take it as a particular value and then put it as a CGB value, CGC or CGB. GB represents the body. We can also call it as CGC channel with respect to the NMOS. But here I've taken it as CG gate to body. Right, so for an NMOS transistor, we have three capacitances, which we have denoted it. One is the input capacitance or the gate capacitance. The other two are the parasitic capacitances, or nothing but the diffusion capacitances, also called as the parasitic capacitances, diffusion capacitances, depletion capacitances. All right. So similarly, we will get for the PMOS, we will get three capacitances, one on the gate side, and then one on the drain side, and then one on the source side. Yeah. So drain side and then the source side. The body for the PMOS is now connected to the VDD. So remember that the body of the PMOS is connected to the VDD. source is connected to the VDD. So my source to body capacitances on both the terminals, I will see the VDD connected. On the drain side, it is connected to the body, rather the capacitances of the drain to body capacitances for the PMOS is denoted here. And whereas on the input side, we will have the gate to body capacitances of the PMOS. Right, so the body is connected to the VDD, and that's why the VDD terminal is here, and the other side is connected to the gate. Right, so now I have the capacitances. So looking into the capacitances, so if I have any kind of a capacitances in the circuit, we know that there will be charging and discharging effect, and the charging and discharging profile of 50% should give me, the propagation delay falling and propagation delay rising values. So that's why the capacitances, realizing the capacitances in a digital circuit is very, very crucial. Right, so this is there's some of the definitions which we have anyway seen. CSB represents source to body capacitance, gate to body capacitances, and then drain to body capacitances. Okay, hope this is clear. So moving ahead, so I've drawn here, this particular portion of the circuit is taken from the previous slide. On the right hand side, I've drawn two capacitances. So let's have a closer look at it. The CDN here at the output side. So this is my output. For an inverter, we know that the drains of the PMOS and then the drains of the NMOS are tied together. So that is the output. And then one capacitance is CDB, drain to body capacitances of the NMOS, and then drain to body capacitance of the PMOS. So this is the drain to body capacitance of the PMOS, and then this is the drain to body capacitance of the NMOS. On one side it is connected to the ground, the other side it is connected to the VDD. And I've also written that in a transient AC analysis, all the DC sources are, if I want to do a transient analysis, especially if I'm looking at the capacitances, charging and discharging profile, or rather the output, whether it is rising or decreasing, and then estimating the propagation delay falling or rising, right? Looking at that particular 50% point in the output voltage profile, then actually we are doing a transient analysis, right? So this is basically the transition from 0 to 1 volts, transition from any change in the input voltage should give me a change in the output voltage to reach to a steady state value. Right, so before reaching the steady state value, we are doing that kind of a transient analysis. So for any kind of an AC analysis or a transient analysis, what we say is the DC sources should be considered as a ground, right, for any kind of an AC or a transient analysis. That is one way of looking at it, and then trying to estimate the propagation delay parameters. But what really happens, we will see. So when the output voltage is actually 0, right, for this particular circuit of the drain to body capacitance and drain to body capacitances for the PMOS and NMOS. For the NMOS, it is connected to the ground here. For the PMOS, it is actually connected to the VDD. Right. So when it is actually 0, this particular capacitance, a CD, drain to body capacitance of the NMOS, is on both the terminals, it is 0, so it is not at all charged. So the charge for that particular capacitance is 0, so the voltage is actually 0. Whereas the CDB here for the PMOS, right, so the output voltage is 0, and on the other terminal it is VDD, so it is kind of completely charged. It is kind of completely charged to minus VDD value. So if I take a KVL, so this particular Vout value turns out to be 0, right, when Vout was 0. Now, when we switch to 1 here, when the output voltage switches to 1, for an inverter, when the output voltage switches to 1, that means that the input side, there is a change. There is a change from 1 to 0 at the input side. And that's why we get an output voltage change of 0 to 1, right? So when the output voltage changes from 0 to 1 here, this particular capacitance, the CDB capacitances, this particular capacitance starts charging. And this particular output voltage, of course, when it changes from 0 to 1, slowly it charges. So my output voltage profile is going to have some kind of capacitor charging profile, right? So from 0 to 1, right, for this particular capacitance. This particular capacitances, once the output voltage reaches to 1, that means the VDD value here, what it really happens is the capacitances here right? Whatever the charge it has accumulated, it should actually go away. All right. So what it means is the voltage across this CDB of PMOS, the drain to body PMOS, should be the 0 volts. So what it really means is this particular capacitance, this is actually discharging, right? And this particular capacitance, the NMOS drain to body capacitance is charging, the PMOS drain to capacitance is actually discharging, right? So that's what is happening. So in fact, what we can say is effectively we can consider both the capacitances, because both the capacitances are in parallel, and if I actually take it with respect to the ground, and both the capacitances will be parallel, because effectively we are actually supplying the same kind of a charges on the both the sides. So if I go back to the slide number 7, you will see that here the moment it goes higher, the output voltage goes higher, it is providing the positive charges. Here also it is providing the positive charges, so that on both the sides of this capacitance it will neutralize, and then it is kind of considered to be completely discharged. Right here also it is applying the positive ions, and thereby we'll get this capacitance to be charged. Right, so it is actually in a way both the capacitances we can consider that it is actually charging. Effectively it is having the same process. One is discharging and another one is charging, but effectively the process is the same, and output voltage is actually increasing from 0 to 1, whatever the profile, maybe an exponential profile or whatever the linear profile. It starts from with respect to time, it starts from 0 and then eventually reaches to a value of 1 volts, right? But effectively it is coming from both the capacitances, right? So that's why we have drawn an equivalent capacitances of the two parallel capacitances, right? The equivalent of the two parallel capacitances is nothing but the summation of those two capacitances. Right, so we come back to this particular circuit of an inverter, where we notice that I can actually take capacitance of drain to body of PMOS and drain to body capacitance of the NMOS. I can actually have an equivalent capacitances and tie it together as CDBP plus CDB of N. Here, one more addition is done. The output actually here, the output of this particular capacitance is connected to another inverter. Right, it is actually connected to another inverter, where the another inverter's input capacitances, CGS, of course this B is not there, this S is not there, this B is there, CGB of NMOS2, this is another inverter, so this is the second inverter, and this is the first inverter, right? So here also we had the input capacitance of gate to body of the PMOS and NMOS, and I've written a subscript of 1 representing this is the first inverter. The second inverter, we will have the same notation, CGB of PMOS of 2 and CGB of NMOS of 2 for the second inverter. So now at the output Y node, I now have 4 capacitances, CDB P1, CDB N1, CGB P2 and then CGB N2. And I've also included the wire capacitances here. So there is a wire capacitance, right? So a wire can always be modeled as a capacitance, assuming that there is a copper wire going along. And then there is it is complete, the region is completely encapsulated or insulated with the silicon dioxide. And on the bottom side, there is one more wire that is going along. So we will have this as is, the wire is kind of modeled as a capacitance. So I have also considered or accommodated in this particular C wire model capacitance. So now I have at the output node, I have this 5 capacitances. So 1 capacitance, 2 capacitance, 3 capacitance, 4 capacitances, and then the 5th capacitances. All put together, I can actually have a C load capacitance at the output node. Remember that another information, the the source to body of NMOS, source to body of the PMOS are connected to the same potential. So even if the output changes here, even if the output changes from 0 to 1 or 1 to 0, this will not have any effect. So this particular capacitance, right, we can actually ignore, This particular capacitance is on both the terminals, it is ground, and if the output changes, there won't be any effect. So this also we can ignore. So the 5 capacitances I can consider at the output node. So this is what we have. So finally, we have the first stage inverter. And if I really want to find out how much, how much time it has taken at the output node, if given the change in the input, the output changes. And what is the propagation delay falling and or the propagation delay rising? It is actually dependent on all this 5 capacitances, 1, 2, 3, 4, and 5, which we put it as a C load capacitance. Right, so this is about the first stage. Of course, there will be a second stage also because we have drawn that. And if I actually take the second stage output, if I actually probe the second stage output, I should be able to characterize the propagation delay falling and rising for the second stage as well. Right, but we are at this particular point of time, we are interested in the first stage output, how it is changing with respect to the change in the input voltage. Right, so hope up till this point of time it is clear. So what we had seen was completely a different module on the delay. We understood the definition of the propagation delay and the contamination delay, falling and then rising, and then we started looking at the inverter circuit, understood all the capacitances, the input capacitances, and the parasitic or the depletion capacitances, and especially how the depletion capacitances for the output node can be made as an equivalent capacitances, because all these capacitances are in parallel, and for the transient or an AC analysis, even if it is connected to the VDD, we consider that to be, all the DC sources are considered or represented to be the ground potential. So finally, we have the first stage inverter, even if it is cascaded to the next stage inverter, the first stage inverter output sees 5 capacitances altogether, including the wire capacitance. So what we have done is we have determined an equivalent capacitance called the C load capacitance.